This video discusses the most fundamental trigonometric identities. These are the ones that you're going to use the most. These should be your go-to. They're also the easiest of all the identities. These are also identities that would not be provided on any type of formula sheet for an exam. So first we have our reciprocal identities. We've seen these before when we first introduced our basic trig functions. So we know that sine of theta and cosecant of theta are reciprocals of each other. So sine of theta equals 1 over cosecant of theta, and cosecant of theta equals 1 over sine of theta. Cosine and secant are reciprocals of each other. Cosine of theta equals 1 over secant of theta. Secant of theta equals 1 over cosine of theta. And tangent and cotangent are reciprocals of each other. Tangent of theta equals 1 over cotangent of theta. Cotangent of theta equals 1 over tangent of theta. Our next three are our Pythagorean identities. These are used very, very frequently. The most basic Pythagorean identity is the first one, sine squared theta plus cosine squared theta equals 1. You're going to use this all the time when we get to verifying trigonometric identities and solving trigonometric equations. The other two Pythagorean identities can be derived from the first. Honestly, I only ever remember the first one, sine squared plus cosine squared equals 1, because I can derive the other ones. So let me show you how to do that. And I'm going to have bad notation here, just abbreviating. So if we have sine squared plus cosine squared equals 1, if I go through and I divide each one of these terms by sine squared, which is a legal math move because I'm dividing both sides of the equation, all terms, this is going to simplify and give us 1 plus cosine over sine is cotangent, and then 1 over sine is cosecant. And that gives us the third of the Pythagorean identities. I can derive the second one in a similar fashion. So I'll do that over here on the right. Again, starting with sine squared plus cosine squared equals 1. This time, I'm going to divide each term by cosine squared. Sine divided by cosine is tangent, that's squared. Cosine squared divided by cosine squared is 1, and 1 over cosine is secant, so this here will be secant squared, and that gives us the second of the Pythagorean identities. So again, I only memorized the first one, knowing that I can easily derive the other two, and honestly, it's the first one that we are going to use 80% of the time. Next, we have our quotient identities. These ones are familiar already to us as well. Tangent of theta equals sine of theta over cosine of theta, and cotangent of theta equals cosine of theta over sine of theta. Frequently, we like things written in terms of sine and cosine just because we do most of our work with that, and that's when the quotient identities really come into play for us. Negative angle identities are next. So here we have that sine of negative theta equals negative sine of theta. These are identities that I don't memorize very much. I just think about what's happening and then I don't have to memorize. In trigonometry, there are so many formulas, and trying to memorize them all is an impossible task. So if we can really understand where things are coming from rather than just rote memorization, it's going to help us remember more and understand deeper, which is really the point of it all. Okay, so here I have this little diagram where I have made angle theta. So I had an angle in standard position, so theta going up and then negative theta going down, equal measure. So if I look at those two triangles, I see that the x value stays the same. See, they're both positive because we move to the right, But the y values are opposite. When we're in the first quadrant, that y value is positive, but in the fourth quadrant, that y value is negative. And r, our radius, is always positive. So I think about sine, and sine is equal to y on the unit circle. So what happens to the y value when I do an angle of theta versus an angle of negative theta? And we can see on this diagram that our y value has an opposite sign. So that leads us to the conclusion that sine of negative theta is equal to negative sine of theta. Now, looking at cosine, cosine of negative theta equals just cosine of theta. Because if we look at our two triangles, we see that for both of them, the x value is positive. So whether our angle is positive or negative, the x value doesn't change sign. So I use the diagram to help me think about sine and cosine, and then I can just get the others from that. So sine and cosecant are reciprocals of each other. Reciprocal means just flip over the fraction. It doesn't mean to change the number from positive to negative. So sine and cosecant follow the same rule. Similarly, cosine and secant, they follow the same rule because they're reciprocals of each other. Now tangent, again, I use my diagram. Tangent I know is y over x. And in the first triangle, y over x is positive, but in our second triangle, in the fourth quadrant, y over x is negative. So that leads us to the conclusion that tangent of negative theta is going to be negative tangent of theta, because in the first quadrant we got a positive, and in the fourth quadrant we got a negative. And then cotangent is simply the reciprocal of tangent, so it's going to follow the same rule. I know that some students simply remember that all of them switch to negative except cosine and secant. I'm hoping that you understand it on a deeper level and don't just memorize it that way. All right, so now let's use these identities to do something. Let's find sine of s using the Pythagorean identity given cosine of s is equal to 3/4, and our angle s is in quadrant 1. Okay, well, our Pythagorean identity says sine squared s plus cosine squared s is equal to 1. So let's plug in what we know. Sine squared s plus, remember that cosine squared of s is the same as cosine of s squared. So this becomes 3/4 squared equals 1. Cosine squared s plus 9/16 equals 1. Subtracting 9/16 from both sides, we get sine squared s equals 7/16. And as I mentioned with our notation, I'm going to go ahead and change this. This is going to be sine of s squared equals 7/16. Now we can apply our square root property and take the square root of both sides. On the left, the square and the square root cancel out, leaving us with just sine of s. But on the right, since we did square root property, we're going to get plus or minus the square root of 7/16. The square root of 7/16 simplifies down to the square root of 7/4. And now we need to determine whether we want the plus or the minus or both. The directions told us that our angle S was in quadrant 1. So is sine positive or negative in quadrant 1? Well, it's positive. Right, so we're going to throw out the negative and we get a final answer that sine of s is equal to the square root of 7 over 4. I gotta admit, if I was just asked to do this problem without being told specifically that I had to use the Pythagorean identity, I would not use the Pythagorean identity. I would have just drawn myself a triangle in the first quadrant, having an x value of 3, an r value of 4, did Pythagorean theorem to get my y side, and then just said that sine was y over r. But we wanted to follow directions. It's important to see that we can, get the same answer using different techniques. But please know, if you're just asked to do this without being told you have to do Pythagorean identity, way easier to do that triangle work over on the side. Next, we are going to write the first trigonometric function, cotangent of x, in terms of the second trigonometric function. Doing this is very helpful when we are verifying trig identities and solving trig equations. So we want to start with cotangent and end up with just sine. So what do we know about cotangent of x? Well, it's the reciprocal of tangent. That doesn't help us get a sine. Using our quotient identity, cotangent of x can be rewritten as cosine of x over sine of x. Good, we're halfway there, right? Denominator sine, but I need to turn that cosine into sine. This is one of the times where we use our Pythagorean identity. This is very common that we do this. So our Pythagorean identity says sine squared plus cosine squared equals 1. I'm going to solve this equation for cosine. So let's subtract sine squared from both sides. Gives us cosine squared equals 1 minus sine squared. And then I'm going to take the square root of both sides. And we get that cosine of x is equal to the square root of 1 minus sine squared x. Because we want it for algebraic purposes, we're not going to put the plus or minus there. We're just taking the principal root. So cotangent of x can be rewritten as the square root of 1 minus sine squared x all over sine. It can be tempting to want to simplify that sine squared under the square root, but we cannot do that because there is a plus or minus sign underneath the radical. It might also be tempting to simplify the two signs, but we certainly can't do that either because one's under a radical and one is not. In our next example, we want to rewrite the expression in terms of sine and cosine only. So let's start with secant of theta. We want to rewrite it just sine and cosine. So secant is going to be 1 over cosine. And then we have cotangent. Cotangent is cosine of theta over sine of theta. And then we have times sine of theta. I'm just going to put that over 1 so everybody's a fraction. And now we want to simplify as best we can. Notice that cosines cancel out and sines cancel out. We're actually left with just 1. Let's do the same thing for the next example. Let's rewrite it in terms of sine and cosine only. There's 2 different ways that we could approach this problem. We could rewrite secant as 1 over cosine right away, but then we're going to have to multiply out, and I don't know. I'd prefer not to multiply out a fraction if I don't have to. So I would recommend multiplying this out first, just to get that out of the way, and then rewriting it in terms of sine and cosine. It'll just make our multiplication easier. All right, let's multiply this out. Secant times secant, secant squared theta, secant times 1 plus 1 secant. -1 times secant minus secant of theta, and then a -1 times a +1 minus 1. Well, our secants in the middle are going to cancel out, and we're left with secant squared theta minus 1. And then from here, we have two options kind of as well. So I like to show you both, so whichever one your brain feels more comfortable with, that's the route I want you to take. So the first thing we could do is we could just jump to rewriting secant in terms of cosine. Oh, secant squared is going to be 1 over cosine squared. And then we want to simplify by adding or subtracting these two. So we'll have to get a common denominator of cosine squared. So this becomes minus cosine squared over cosine squared, which then gives us 1 minus cosine squared all over cosine squared. So that's one good option. But from here, we have another option on what we could do. Secant squared is part of a Pythagorean identity. Tangent squared plus 1 equals secant squared. So if I subtract 1 from both sides, I get that tangent squared is equal to secant squared minus 1. So when we see that secant squared minus 1, we could just replace it with tangent squared. So our other option would be from that point to go to tangent squared theta. Remember, we're ultimately trying to write in terms of sine or cosine. Tangent is sine over cosine, so this would become sine squared theta over cosine squared theta. So that could be another option for us. And these are equivalent expressions because we know from the Pythagorean identity, our first one, that sine squared theta is equal to 1 minus cosine squared.